Welcome to Engineering Knowledge. We are discussing design of IIR filter from analog filter in the last video session, and we have already compared the analog and digital domains using these characteristics. So we are not revising here, just putting the slide to remind you. And it is the next slide. It was the next slide, that is analog filter system function, which can be represented using poles and zeros, or it can be represented using linear constant coefficient differential equation. It was already discussed in previous video, so just to remind you the results. And next was desired property of effective conversion technique, that the geom axis of analog filter S plane should map onto the unit circle of Z domain, and left hand side of the S plane poles should map into the inside the unit circle. These are the desirable properties. These three slides which we have already discussed in detail in previous video. So now we will move forward by using the second method, that is IIR filter design by bilinear transformation method. We know in the impulse invariance method there was some mistakes, there was some disadvantage that there was many to one mapping in the impulse invariance method, because due to this many to one mapping there was aliasing, and it is only used for low pass filter and band pass filter. It cannot be used for high pass and band reject filters. It is the disadvantage of impulse invariance method. But in bilinear transformation we remove this disadvantage by using many to one mapping. It is a conformal mapping that transforms the geom axis, complex axis, S-plane complex axis into unit circle in the Z-plane only once, thus avoiding aliasing of frequency component. It is one-to-one mapping using frequency warping concept. We use the concept frequency warping here. Now suppose to derive the method, let single pole analog filter is taken. Easiest case, Hs is equal to B upon S plus A, single pole, be some constant. And it is always H transfer function is always equal to output upon input, Ys upon Xs. So we can cross multiply this transfer function, single pole analog filter. We will cross multiply and do some inverse Laplace transform. Then have the equation, that is S, using the differentiation property of Laplace transform, Sys becomes d by dt yt, Ays becomes Ayt, Bxs becomes Bxt. Here we have used differentiation property here. Now it is what first order linear differential equation, which corresponds to single pole analog filter. Now first step is integrating for one sampling time. Integrate this equation for the one sampling time, that is n-1t to nt. Integrating n-1t to nt, nothing extra. We have just integrated there are three parts, 1, 2, 3. So 1, 2, 3 parts are integrated, now combined. And further we will use trapezoidal rule for integration, and this rule says that for integration a to b of any function fx dx will be approximately equal to b minus a, difference between the limits, into fa plus fb by 2. So this formula, this trapezoidal rule for integration is used while integrating the term second and third only. First term is integrated as usual. The integration and differentiation is now cancelled out. It becomes yt, and yt is now putting the limits ynT minus yn minus t. It is a simple integration method. In the second and third method we use this method, trapezoidal rule of integration, that is a is constant, n minus 1t to nt yt dt. Now further use the equation, that is difference between the limits n minus 1t minus nt, and putting the value fa plus fb, first fa then fb, that is yn minus 1t or n plus n y n t. Both are added by 2. In the third term also b is constant, difference between the limit, and first x is put by x nt, then x n minus 1t by 2. So second and third are solved by trapezoidal rule of integration. Combining three terms in the equation, we have this equation again, yn minus ynt minus yn minus 1t plus at by 2, because a is here. And from this equation we have the t, because n minus 1t minus nt will become t, and it is 2. A t by 2 ynt plus at by 2 yn minus 1t. Okay, second term. Third term is again b This term is t and it is 2 bt by 2 multiplied with xn t plus bt by 2 multiplied with xn minus 1 t. Okay, this is the simplest equation after getting the integration, and further we will do first we will do z transform, but we know that y and t is generally written as yn, whereas x and t is generally written as xn, because t is nothing but the sampling time period, which is not always written. Okay, so just taking the t out in representation, it becomes yn, it becomes yn minus 1, it becomes yn, it becomes yn minus 1, it becomes xn, it becomes xn minus 1, and applying the z transform, after z transform, yn becomes yz, yn minus 1 becomes z inverse yz, this is constant, yn becomes yz, yn minus 1 becomes z inverse yz, this is constant, yxn becomes xz, constant, xn minus 1 becomes z inverse xz. So every term is doing the same by applying the z transform, and simply in this equation you can have the all yz common and all xz common, and taking out yz upon xz on one side of equality, xz is equal to yz upon xz equal to all the term of xz and all the terms of yz. Okay. And further we can represent this equation by using the bt by 2 common 1 plus z inverse, and here at by 2 is common, taking out in these two terms, and at by 2 becomes 1 plus z inverse. Further multiplying and divide by t by 2 1 plus z inverse, this term multiply and divide, so b, here b will become, and here you will multiply and divide here and here also, and it will become t by 2 1 plus z inverse will be gone, so it becomes only a. So after multiplying and divide by t by 2 1 plus z inverse, it becomes this equation. You can check it, multiplying this term, divide this term, divide this term, divide this term, and this is for the hz, that is digital filter. And comparing the starting value, that is we have the analog filter, single pole analog filter, b upon s plus a. Now it is transformed by bilinear transformation, becomes b upon 2 by t 1 minus z inverse upon 1 plus z inverse plus a. So after comparing this transformation, it is easily seen that this s is now become this 2 by t 1 minus z inverse upon 1 plus z inverse term. Okay, so it is what bilinear transformation. After comparing these two results, we have just concluded that s equal to 2 by t 1 minus z inverse upon 1 plus z inverse. This condition is known as bilinear transformation. So simply just have the hs and put the every s in this value, and you have the required hz using bilinear transformation. It is very easy method. Again, the mapping concept and frequency warping in bilinear transformation. We know that s equal to 2 by t from the last expression, 1 minus z inverse 1 plus z inverse. Further it can be written as z minus 1, z plus 1, z inverse is 1 upon z, z inverse is 1 upon z. You can put it here, and you have this equation also. And you know that from the identity, z equal to r e raised to power j omega, s is equal to sigma plus j ohm, complex plane, analog filter and digital filter, and z plane. Putting these two identities in these equations, that is from here, s is put here sigma plus j ohm, and z is put here r e raised to power j omega, r is j omega. Okay, putting these identity here, and using the Euler's formula says that e raised to power j omega is equal to cos omega plus j sin omega. Putting the Euler's formula and do some rationalization. I have not done here. Do some rationalization and separate the real and imaginary parts, and further comparing the real part with sigma and imaginary part with ohm. Okay, that is sigma is equal to this, and ohm part is 2 by t 2r sine. It may be called as omega sometimes, but because it is also omega, so not to be confused with omega. I can call it ohm or omega. Further, it can also call it omega or w as suitable. It is nothing important, because it is the representation of analog and digital frequencies. So ohm is equal to 2 by t 2r sin omega, 1 plus 2r square plus 2r cos omega. Okay, these two are again the mapping, which says that when r is equal to 1 or sigma is equal to 0, then r is equal to 1. For this complex values lie at the complex plane, sigma equal to 0, all the values map on the unit circle boundary. If sigma is equal to less than 0, then r is equal to less than 1. It means left hand plane it means left hand plane will map into the inside the circle. R is less than 1. If sigma is equal to greater than 0 positive, that is right hand spread plane, then R becomes also greater than 1. It means outside of unit circle. So right hand plane mapped outside the unit circle, left hand plane mapped inside the unit circle, and on the complex plane map on the unit circle. So it is from this formula only. Now further we have to find the frequency warping concept basically. So for that concept we will use this relation, sigma ohm is equal to 2 by t 2r sin omega 1 plus r square plus 2r cos omega. Putting the special case of r equal to 1, critical case, when r equal to 1, sigma equal to 0, and ohm becomes 2 by t. Putting r equal to 1, 1, 1, 1 plus 2 cos omega, and it becomes 2 plus 2 cos omega, and 2 can be taken out. 1 plus cos omega, 2 cancel out. It becomes 2 by t sin omega 1 plus cos omega. Further, this is the formula by trigonometric identity of tan omega by 2. Okay, we are just using the identity of trigonometric, and it becomes 2 by t tan omega by 2. This is the final expression, and this expression says that ohm is equal to 2 by t tan omega by 2, or further we can see that omega is equal to 2 tan inverse ohm by t by 2. Just inverting the value and finding the omega and plotting this omega curve with respect to ohm t. We will have this because of this tan inverse function, we have this plot. Okay, and this is the plot of basically tan inverse arc tangent. Okay, so we can see that all the values of minus infinite to infinite ohm and analog frequencies are mapped onto the range of minus pi to pi. This range, in this range, all the frequencies of infinite angular frequency are mapped. But what happened here? When frequencies are higher, then these are compressed in digital domain. When frequencies are lower, then these are expanded in digital frequency domain. Okay, higher frequencies are compressed, lower frequencies are expanded in digital domain. So this is known as lower frequencies analog domain are expanded, higher frequency analog domain are compressed in digital domain, and this is known as frequency warping concept. That is, here entire range in analog frequency is mapped only once into the range minus pi to pi. This mapping is non-linear, obviously. Looking at non-linear, because linear function will be straight line. A frequency compression or frequency warping is observed. That is frequency compression here. Frequency compression. Frequency compression or frequency warping is observed due to non-linearity of tan inverse function, and this property is due to that tan inverse property, because tan inverse graph is like that. So it means that points at s equal to infinite, when frequencies are infinite, it will be mapped at minus pi, minus 1. When s equal to infinite, then it will be mapped at z equal to minus 1, because now s here is omega is given. Okay, so this is the frequency warping concept, that frequency compression at higher frequency and frequency expansion at lower frequency, and with respect to and digital frequency. Analog frequency and digital frequency are related with frequency warping concept. Now an example, HAS suppose is given s plus 0.1 upon s plus 0.1 square plus 16 or 4 square, when omega r resonant frequency is given as pi by 2, suppose, then omega r can be used to find using this formula, that is omega r is equal to pi by 2, and this is frequency transformation, frequency warping formula, omega r 2 tan inverse omega t by 2, and suppose it is, and then this, in this case we will compare this expression with the standard expression of analog filter, that is s plus a upon s plus a square plus ohm square, that is ohm square. Comparing this value, we have found out that analog frequency is 4, because this term is ohm square. So ohm, now further, after putting the omega r to pi by 2 and ohm is 4, we can find t is equal to, from this formula, t equal to 1 by 2. Now using the bilinear transformation, we know that s equal to 2 by t 1 minus z inverse upon 1 plus z inverse. So just, it is very easy, because just put the value of s everywhere using this formula, nothing else. T is put here 1 by 2, so it becomes 4. Okay, t is 1 by 2, 2 by t becomes 4, and putting the values and solving the values obviously and finding the answer. And it is a digital filter corresponding to this analog filter using bilinear transformation method. and it's all about bilinear transformation. In next video, we will study design of Butterworth filter and digital filters Butterworth filter using bilinear transformation method. And thank you very much for watching.